So magnetic flux is nothing but the magnetic lines of force crossing per unit area. Okay. So this is how the magnetic lines of force. Okay. So magnetic flux is defined as the number of magnetic lines of force in a magnetic circuit, we can say, is called the magnetic flux. Its SI unit is Weber, or say volt second. Its CGS unit is Maxwell. It is denoted by say phi m. Okay, m for magnet. The magnetic flux measures through flux meter. जैसे हमने इलेक्ट्रिक फ्लक्स पढ़ा है वैसे ही ये मैग्नेटिक फ्लक्स. ओके, लेकिन यहाँ पर मैग्नेटिक फ्लक्स इज ए डिफरेंट फ्लक्स, तो देयरफॉर इट इज डिनोटेड बाय phi m. तो phi इज इक्वल टू डबल इंटीग्रेशन ऑफ b डॉट ds. जैसे b हमने डिफाइन किया था, तो मैग्नेटिक फ्लक्स पर यूनिट एरिया. ओके, तो मैग्नेटिक फ्लक्स इज इक्वल टू इंटीग्रेशन ऑफ b डॉट ds. ds यानी क्या है? एरिया है, like this. So phi is equal to say ba cos theta. So cos theta is the direction between the field lines and the surface, and a normal to the surface. Okay, phi is the magnetic flux, b is the magnetic field, a is the area, and theta is the angle at which the field lines pass through the given surface area. Okay. Now magnetic flux density, as I have defined, it is magnetic flux density means magnetic flux crossing per unit area. We have already defined that. So B is equal to simply phi upon A. The force acting per unit length, per unit current on a wire placed at right angles to the magnetic field. We can define like this also. The force acting per unit length per unit current. Okay, so if a wire carrying current, then it will produce a magnetic field, and that magnetic field produces a magnetic force. The force acting per unit length per unit current is called the magnetic flux density, you can say. So F is the total force acting on a wire, L is the length of the wire, I is the current flowing through the wire. The SI unit of B is, already we know it is Tesla. That is equal to kg per second square per ampere. In CGS units, B is Gauss. Okay, and what is the relation between Tesla and Gauss? 1 Tesla is equal to 10 to the power 4 Gauss. Okay, B is also a vector quantity. So magnetic flux density can also be denoted by this. As I said, B is equal to phi by A, Y is equal to B into A. The diagram shows the magnetic flux is crossing that area. Okay, so here the flux is large, here the flux is small, because the number of lines crossing per unit area is very small. Here the number of lines crossing per unit area is very large. Then if this wire is carrying current I, then at a distance P, okay, at a distance T, the flux will be now out of page. Out of page means this side. Okay, and here at this side the magnetic flux will be inside page. Okay, so that is the magnitude and direction of the magnetic flux. Again, so we have already seen the let us see the Faraday's laws of electromagnetic induction. So Faraday's laws of electromagnetic induction: the change in flux induces EMF. So this is the magnet. This is the magnet. If it moves, then this is the coil. Okay, yellow color coil is there. There is a voltmeter. Okay, so when magnet moves, the flux linked with this coil will change, and that will produce, or say that will induce EMF in the coil. Okay, But when the motion of magnet is stopped, then there will be no induced EMF across this coil. Only when the motion is running, then only the voltage is appeared, or say EMF is induced. Okay. If you keep the magnet fixed, that means the magnetic flux linked with this coil is fixed. It is not changing. Then there will be no EMF. Okay. In a similar way, if you move the magnet away from the coil, then also we can get the EMF. Either you move towards the coil or you move away from the coil, there is a change in flux linked with that coil, and that change in flux induces EMF. If you keep the magnet fixed position, at fixed position, the magnetic flux linked with coil is not changing, therefore there is no EMF. So E is directly proportional to d phi by dt. D phi by dt is rate of change of flux. Okay. And this rate of change of flux induces EMF, and that is equal to minus, that opposes the EMF. It will change the induced EMF opposes the change in flux. So that is the minus sign, and that minus sign is induced by the Lenz's law. So therefore E is equal to, say, minus k d phi by dt. So k is a proportionality constant, and we take this proportionality constant as a 1. Okay, so k is equal to 1. So therefore finally you will get E is equal to minus d phi by dt. So this is combinedly one may known as the Faraday's Lenz's law. So come to the next point, E is equal to minus d phi by dt, but phi is equal to an integration of b dot ds. Okay, phi is equal to integration of b dot ds. So therefore, if you put the value of phi in the equation, then you will get the equation like this. So if you take this d by dt inside, so that will be like this. Then, so this is called the integral form of Faraday's law. So this form of equation. So up till now you just know this equation only. Okay. This is the simplest form of electromagnetic induction. But just now we have studied that phi is equal to double integration of b dot ds. Okay. Then if you combine these two equations, you will get this type of equation, which is the Faraday's law. Okay. And this is the integral form of Faraday's law. So let us see the differential form of Faraday's law. So we know that from electrostatics, E is equal to line integral of E dot dl. We have already seen in the electrostatics. Okay. Or say simply, electric field is the ratio of potential upon length. Okay. Potential per distance is the electric field. Therefore, E is equal to line integral of E dot dl. Though by applying the Stokes law. Okay. So what is Stokes law? You have to remember this Stokes law. Stokes law relates the line integral to the double integral. So E dot dl, line integral of E dot dl is equal to double integration of curl E dot ds. So you have to remember this Stokes law. So after conversion, what happens? After conversion, curl of E is equal to minus dB by dt. If you replace this single integral by the double integral, so ds cancels. If you compare these two equations, so ds cancels. So both are the double integrals. And one may write curl of E is equal to integrand curl of E is equal to minus dB by dt. So this is called the differential form of the Faraday's law. So curl of E is equal to minus dB by dt. So both are the Faraday's laws. Okay. So this is the differential form of Faraday's law. Self-induction. So when current flows through the coil, so there is a coil as shown in figure. When the battery is connected, current flows, and that current will flow in a circular path as shown in the diagram. Okay. So there is a change in current. And therefore, as the current changes, the magnetic flux induced with the coil will change, and that will change the EMF. Okay, that will induce the EMF as per the Faraday's law. Is that clear? When current through the coil changes, the magnetic flux linked with the coil changes, and EMF induced in the coil, which opposes the change in current, which we have already seen. So this is called the self-induction. So self-induction means induction of EMF in the same coil due to the rate of change of current in the same coil. Okay. This phenomena is called the self-induction. Change in flux is directly proportional to change in current. Okay. So we can say phi is equal to L into I. So L is a proportionality constant, which is called the coefficient of self-induction or simply self-induction. So E is equal to minus d phi by dt. Okay. So E is equal to minus L di by dt. Okay, because phi is equal to L into I. So therefore E is equal to minus L di by dt. So therefore L can be defined as E upon minus E upon di by dt, that is EMF induced per unit rate of change of current. So self-induction is the ratio of EMF induced per unit rate of change of current. So its unit is Henry, or say voltage per ampere per second. Then let us see the mutual induction. So if you just see the diagram, so there are two coils, coil 2 and coil 1. Okay. So there is a magnetic flux linked with coil 1. Okay, because we are applying the electric field through this coil. Okay. So there is a magnetic flux linked with this coil because we have applied the EMF here. Okay. So there will be change in flux. There will be change in flux linked with this coil 1. But there is another coil where the flux produced by this coil is also linked with this coil 2. Okay. फ्लक्स यहां पर भी है, फ्लक्स यहां पर भी है कि नहीं? तो द चेंज इन फ्लक्स इन कॉइल 1, also there is a change in flux in coil 2 because the flux is same produced by the coil 1. So because of this change in flux in coil 1, the change in flux in coil 1, the EMF is induced in the coil 2. Okay? So because here we have applied the EMF source. So therefore there is a change in flux. This change in flux linked with coil 2 will induce EMF in coil 2. है ना? पहले के कॉइल के चेंज इन फ्लक्स के वजह से दूसरे कॉइल में EMF इंड्यूस हो रहा है. दिस इज कॉल्ड द सेल्फ इंडक्शन. When current flows through the coil 1 changes, the magnetic flux linked with the coil 1 changes, and magnetic flux linked with coil 2 also changes because it is in contact with the coil 1. okay, not physical. And EMF induced in coil 2, which opposes the change in current, of course. Okay. So EMF induced in coil 2 is directly proportional to change in current in coil 1. So EMF induced is equal to di1 by dt. Okay. So M is called the mutual induction. E upon di1 by dt. Okay. Mutual induction, same unit Henry. So that is EMF induced in coil 2 because of rate of change of current in coil 1. Mutual induction. Then we have the transformer, which is the electrical device which depends upon the principle of mutual induction. Okay. So which converts high AC into low AC to high AC, vice versa. Okay. So this is the transformer you might have seen. So this is the laboratory transformer. Okay. This is the diagram where the transformer can be shown like this. Okay. So this is the this is the primary coil. It consists of two coils. One is the primary coil where input can be applied, and this is called the secondary coil where output can be taken. And both the coils are wound on a iron core. This is the iron core which may be used for the magnetic flux. The magnetic flux linked with coil 1 also linked with the secondary. Okay, so that by the phenomena of mutual induction, when we apply input, we can get the maximum output across secondary. This is the simple construction of the transformer. Okay, so this is called the primary, where the input is applied, and this is called the secondary. Voltage across primary is Vp, current through primary is Ip, denoted by, and Np is the number of turns. How many number of turns of primary, that is denoted by Np. And similarly, Is is the current through the secondary, Vs is the voltage across secondary, and Ns is the number of turns in secondary circuit. Okay. So this is the symbol for the transformer. So this is the primary, and this is called core, two lines we have shown, and this is the secondary. Okay. Here the number of turns in primary is larger than the number of turns in secondary. So that depends upon the type of transformer. In case of step up transformer, number of turns in secondary larger than the number of turns in primary. Here in the diagram, it is a step down transformer. So let us see the theory of the transformer. Let us see the phi is the flux per turn. Okay. So we know the number of turns. So let us define phi is the flux per turn. So the total number of flux will be equal to number of turns into flux per turn. So EMF across primary will be equal to minus NP into d phi by dt. Okay. Similarly, EMF across secondary will be equal to minus Ns into d phi by dt. So Es upon Ep is equal to Ns upon Np is equal to N, which is the ratio of, or set simply transformer ratio. Okay. It is a transformer ratio, or say turn ratio. Number of turns in secondary to the number of turns in primary is called the turn ratio. So that is the important factor. Again, we can write like this: voltage across secondary upon voltage upon primary will also be equal to for ideal transformer, power is equal to input power. So in case of transformer, we are applying the voltage or say EMF across primary, and by the phenomena of mutual induction, we are getting the power across secondary, EMF across secondary, and this phenomena occurs through mutual induction, and there is a energy transformation through mutual induction. And if there is no loss of energy, if there is no energy loss, then maximum power can be transferred from primary to secondary. So for an ideal case, input power, so ES into IS is equal to EP into IP. Okay, so therefore Vs upon Vp is equal to Es upon EP is equal to IP upon Is is equal to Ns upon Np is equal to N. Okay, that means current in primary, the ratio of current in primary to the ratio of current in primary to current in secondary is called the turn ratio. So these ratios you have to remember. Okay, so if Ns is greater than Np, okay, if Ns is greater than Np, then it is called the step up transformer where turn ratio is larger than 1. Okay, or say if Ns is less than Np, if Ns is less than Np, then it is called the secondary, step down transformer. N is less than 1. Number of turns in secondary, if it is greater than number of turns in primary, then the step of transformer. Okay, where the output voltage is greater than input voltage. And if the number of turns in secondary is less than the number of turns in primary, then it is called the step down transformer. Okay. Yes. So efficiency of transformer. Efficiency can be defined as the output power. It is the ratio of output power to the input power. Okay. So that is equal to PO upon PI is equal to ES into IS upon EP into IP. So percentage efficiency generally defined is it is shown by eta is equal to output power upon input power into 100%. For ideal case, efficiency is 100%. Transformer losses. Even though we have say for the ideal cases there are no losses, but practically there are some losses which may occur in the transformer. Okay, let us discuss one by one. So first type of loss in transformer is copper loss. Okay, so copper loss means the primary coil, secondary coil has some resistance. Ideally it should have negligible resistance, but it will have some resistance. It will not be zero. So therefore heat produced is given by I square R. So some amount of heat is produced in the primary and secondary coil because of their resistances, and this is called the copper loss. Eddy current losses. So we know that the primary coil and secondary coil is wound on a iron core. Okay. So when there is a change in flux linked with the iron core, the eddy currents are produced. That means some energy is lost in the form of producing eddy currents, which is not required, which we don't want. Okay, so that type of loss is called the eddy current losses, and this eddy current losses can be minimized if you take the core, iron core, in the form of laminas. Okay, so as shown in figure, soft iron core, it is in the form of laminas. Okay, so this is as shown. These are in the form of, this is not the complete piece, but it is in the form of laminas. So these laminas may reduce the eddy current losses. Magnetic flux leakage. We know that the concept of mutual induction is the flux linked with primary is linked with secondary. Okay, so here the arrangement is to link the same flux that is produced by the primary. But even though there is some flux leakage, not 100% flux linked with the secondary, which is produced in primary. Okay, so that magnetic flux may produce some loss. So it may not be 100% linked with the secondary. Okay. Hysteresis losses. This is the fourth type of loss. Hysteresis loss means, so there is a complete magnetization and demagnetization of soft iron core. Okay, so this cycle of magnetization and demagnetization may reduce some energy, and this energy is called the hysteresis loss.
सर
Yes.
सर ये जो चारों लॉसेस है ये एक टाइम
Yes.
पे एक ही होते हैं या फिर चारों होते हैं, ऐसा कुछ है क्या?
Means
सर मीन्स जैसे एक टाइम पे एक ही लॉस होगा या फिर एक
मतलब
साइमल्टेनियसली एक टाइम पे चारों हो सकते हैं?
ये चारों भी हो सकते हैं एक टाइम पर, ये अलग अलग है ना,
हाँ, यस सर।
क्योंकि कॉपर लॉस क्या है, रेजिस्टेंस से रिलेटेड है कि नहीं।
यस।
दूसरा लॉस क्या है, एडी करंट का है, वो अलग प्रॉपर्टी है। हीट की अलग प्रॉपर्टी है, एडी करंट की अलग प्रॉपर्टी है, मैग्नेटिक फ्लक्स की अलग प्रॉपर्टी है, हिस्टेरिसिस की अलग प्रॉपर्टी, ये सब फिजिक्स ही है ना, तो वो एक साथ ही वर्क करेंगे, एक साथ ही होगा ये।
थैंक यू सर।
हाँ हाँ, और इसको रिड्यूस भी कर सकते हैं हम। तो आइडियल ट्रांसफार्मर में ये क्या है, रेजिस्टेंस प्राइमरी एंड सेकेंडरी कॉइल शुड बी निग्लिजिबल। जैसे मैंने बताया, अभी देखो आपने पूछा, अभी सॉल्यूशन आ गया, रेजिस्टेंस प्राइमरी और सेकेंडरी का निग्लिजिबल होना चाहिए, सो दैट लॉसेस विल बी रिड्यूस्ड। लॉसेस जीरो तो नहीं कर सकते, लेकिन उसको बहुत कम से कम कर सकते हैं।